Let's talk about the experiment that we're going to be doing this week. We're going to be studying this reaction between the iron +3 and the thiocyanate. And our goal for this experiment is to find the value of the equilibrium constant Kc for this reaction. Now, if you remember, the expression for Kc is shown right here, and it's the concentration of our product over the product of the concentration of our reactants. And it's important to remember that we need the equilibrium amounts. And this is important because what we're going to be doing is we're going to be mixing together some of the iron and some of the thiocyanate. So we'll know those concentrations, but those will be the starting concentrations. We need to know the equilibrium concentrations. So if we think about this from an ice table perspective, if our starting concentrations for the iron are A and for the thiocyanate are B, and we start with none of this product, we can set up the ice table in this manner and find that the equilibrium amounts correspond to these values here. So in order to figure out the equilibrium constant, the only thing we really need to calculate and figure out is X, the value of our product at equilibrium. And this is just a representation of our equilibrium constant with our equilibrium values filled into it. So the question becomes, how do we measure the concentration of this material at equilibrium, this product, or how do we find the concentration of anything at any state in this reaction? Well, we're going to take advantage of the way that our reactants and our products absorb light, because it turns out that our reactants, both of them are colorless, but when our product forms, it gives a red color. So we're going to use that red color to quantitate how much of this product we have. And in order to understand how we're going to do that, we need to think about in a little bit more detail why this product looks red, what's happening to it. And what I have here is a really crude diagram of what happens when a red sample, like our red solution in today's experiment, absorbs light. When the light comes in from a light source, it's a mixture of all the different colors of light. We've got red, blue, green, and many others as well. It interacts with our sample, it passes through the sample, and what happens is the blue and the green get absorbed completely. Some of the red gets absorbed, but not all of it, and the light comes out the other side. What our eye sees is the light that gets through, so it doesn't see any of the blue or the green because that gets absorbed. It only sees the red that comes out the other side. And that is the basis for what we're going to do today. The less light that's transmitted, the more sample we have in here absorbing light. And we have an equation that relates the absorbed light to the transmitted light. It's a logarithmic relationship between absorption and %T. In our experiment today, we're going to measure the %T, but it's really the absorption that we're most interested in, because there's a direct relationship between the absorption, the amount of light absorbed, and the concentration of the sample doing the absorbing. The more that we have in solution, the more light is absorbed. This relationship is called Beer's law, and it says that the absorption, the absorbed light, is directly related to the concentration of the sample and something called the extinction coefficient. That's a constant that determines how effectively our sample absorbs light. So if we think about this, if I can measure the absorption or the transmission, % transmission, and get the absorption, I can find the concentration as long as I know the extinction coefficient. Well, how do I get the extinction coefficient? You'll notice that this is a linear relationship. So if I make a plot of A versus C, my slope will be the extinction coefficient B. And we're going to take advantage of this in today's experiment. There are really going to be two parts to today's experiment. In the first part of the experiment, we're going to measure A, our absorption, at several different concentrations to make a plot and find B, our extinction coefficient, from the slope. And in the second part of the experiment, using the value of beta that we found in part A, we will calculate the concentration at equilibrium of our product for various initial iron plus 3 and SCN minus concentrations. And from that data, we will be able to find our equilibrium constant. There's a little bit of a complication for part 1 that people sometimes get confused by, and we need to talk about this. And that problem is that this is an equilibrium reaction. So if I try to make a solution of my product in order to measure its concentration, so I can make a plot of A versus C, or to measure its absorption, so I can measure plot A versus C. Since it is an equilibrium reaction, it's immediately going to start breaking down into my iron plus 3 and my thiocyanate. This means I don't know how much FeCN plus 2 I actually have left. So we need to find a way to address this. And the way that we address this is by adding a huge amount of the thiocyanate compared to the Fe plus 3 in part 1. So in part 1, the concentration of my thiocyanate is much, much, much greater than the concentration of my iron plus 3 at my initial conditions. Because of this, if we think about this from Le Chatelier's principle perspective, I'm adding a lot of this, shifting to the reaction to my right. That means almost all of my iron plus 3 is converted to product. Therefore, in part 1, the concentration of iron plus 3 initial is approximately equal to the equilibrium amount of my product. Now, it's important to remember that this is the case for part 1 and only part 1. In part 2, we calculate the concentration of our product using the beta we get from part 1 and Beer's law. We calculate, as I said, the concentration in part 2 using beta from part 1 and Beer's law. Then we take our data and find the equilibrium concentrations of everything and find our equilibrium constant.